In this video, we're going to work through several examples that use the fundamental theorem of calculus, part 1. So this is the part of the fundamental theorem of calculus that relates the process of differentiating to the process of integrating. So this portion of the fundamental theorem basically states that when we are taking the derivative with respect to x of an integral, and we're integrating from a, which is a constant, to x, which is a changing value, of some function f of t dt, the process of differentiating here is going to undo the process of integrating, because these are inverse operations. Therefore, we'll be left with the function, which is our integrand. However, this function will be in terms of the upper limit of integration. So you can kind of think of it like this. We'll be left with the function, but it'll be in terms of x. In other words, f of x. And the proof for this theorem was in a previous video. So these examples are just going to utilize this part of the theorem, where taking a derivative of an integral, those are inverses, so they're going to undo one another. So look at example 1. We are asked to find g prime of x for the following functions. And our first example here, our function g of x, is an integral. So if we're asked to find g prime, I'm going to write g prime as the derivative. And notice that g is a function with respect to x, g of x, so therefore we're going to take the derivative with respect to x. So we're taking the derivative of our function g, which is the integral from 0 to x, of the square root of 2 plus t squared dt. So we see that we are differentiating, but we're differentiating a function which is an integral. So these are inverse operations. They're going to undo one another. We will be left with the integrand, the function, which is the square root of 2 plus t squared. However, it will be this function in terms of that upper limit of integration again, the upper limit of integration, which was x, so it's going to be the square root of 2 plus x squared for the value of our derivative. So it's a super simple process. However, the proof is what takes a while to really understand. Again, that's what was in the previous video of showing why this is true. These examples are just showing how we use this part of the theorem. Now, as we move on to our second example here, where g of x is the integral from x to 2, you need to notice that the lower limit of integration is now x. It is not a constant. So once again, it's important to point out when we're using this part of the fundamental theorem of calculus, the lower limit of integration, we write it as a, that needs to be a constant. So for this very first integral, we're going to want to switch our limits of integration. In other words, we're going to interchange them. And we know our properties of integrals. One of those properties says that when we interchange the limits of integration, that means we're multiplying by a negative. So this is going to be the negative integral from 2 to x of cosine of t dt. So I've interchanged my limits of integration so that now my lower limit of integration is a constant. So because I'm being asked to find the derivative of g, I am taking the derivative with respect to x of this function, which is an integral. I almost forgot to write my negative sign. Sorry, let me go back to make sure I have that in there. We're taking the derivative of this function, which is an integral. So because I have that negative, I'm going to go ahead and put this in brackets. So the negative integral from 2 to x of cosine of t dt. Now this negative in front here functions like a -1 times this integral, and we know that when we're taking the derivative of a constant multiplied by a function, that the constant always is just along for the ride, I say. In other words, the constant's just going to be part of our answer. So we're going to have a -1 multiplied by the derivative of the integral. Again, that fundamental theorem says when we're taking the derivative of an integral, those are inverses, so those are going to undo one another. We're going to be left with the integrand, which is cosine of t. However, it'll be cosine of x because that upper limit of integration is x, and our final answer will be in terms of that upper limit of integration. So that leaves me with a final answer of negative cosine of x. Let's take a look at two more examples. We're still finding a derivative in these examples. Now we're finding k prime of w, where k of w is an integral. However, take a look at this integral because these two are slightly different than the previous two that we've done, because now we're not integrating just from 0 to w, but rather we're integrating from 0 to w squared. So it's almost as if instead of having the integral from 0 to some unknown, we now have another function inside this integral as the upper limit of integration. In other words, we have a function inside of another function. And that means that we are going to treat this integral as a composite function. So again, because the upper limit of integration, it's not just a plain w, because it's w squared, it's another function, we're going to treat this integral as a composite function. And remember, anytime we take the derivative of a composite function, this means we're going to need to use the chain rule. So we're taking the derivative of an integral, however, this particular integral is a composite function. Therefore, we are going to use the chain rule when we compute this derivative. So I'm going to write my k prime of w as the derivative with respect to w of the integral that we were given, which was the integral from 0 to w squared of the square root of x plus 2 divided by x minus 4 dx. So once again, I see that I am differentiating an integral. So we see those inverse operations that are going to undo each other. We're going to be left with our integrand, but remember, we're going to take that upper limit of integration that's going to get substituted into the integrand. So instead of the square root of x plus 2, we'll have the square root of w squared plus 2, all divided by w squared minus 4. However, the chain rule says then we must also multiply by the derivative of the inner function. So in this case, the upper limit of integration, which is w squared, is considered our inside function. So we need to multiply by the derivative of w squared, which is going to be 2w. So again, let me write this out the way we used to write it when we first learned to do the chain rule. When we have a composite function, f of g of x, where f is the outer function and g is the inner function, in this case, we're treating our outer function as the integral from 0 to some unknown function of the square root of x plus 2 divided by x minus 4 dx. And then our inner function is that upper limit of integration, which is w squared. So this is how your outer and inner function would look if you're thinking of this as the two pieces of a composite function, which is why if the inner function is w squared, then the chain rule tells us we have to chain on the derivative of that g function. That's where this 2w comes from. And then we would just rewrite this as one big fraction. So 2w times the square root of w squared plus 2, all divided by w squared minus 4 would be my final answer. Now in our final example, our function k is the integral from 3w to the fourth power to 2 of secant x dx. So now we have several problems because first of all, my lower limit of integration is not a constant. So we're going to begin like we did in one of our previous examples by interchanging our limits of integration, which means we will need to multiply by a negative. And that allows the lower limit of integration to be a 2, which is a constant. So that's the integral from 2 to 3w to the fourth of secant x dx. And now the directions say we want to find k prime. So we want to go ahead and compute the derivative of k. So k prime of w will be the derivative with respect to w of the negative integral from 2 to 3w to the fourth of secant x dx. So we're taking the derivative of basically a -1 times this integral. And I didn't mention this earlier in the video, but let me just show it here. I don't think you need to write this down, but really what we're doing essentially is we're recognizing that when we are taking the derivative of that constant multiple, that constant essentially is coming out in front. So it's as if we're taking a -1 times the derivative of this integral. But most people find that it's kind of unnecessary to actually write out that step and then write your next step. So you don't need to write the step that I have written here in red. It's somewhat unnecessary, I think, most of the time. But I wanted to make sure you understand why we're pulling that negative out in front. It's because we're taking the derivative of a constant times a function. So once again, we see that we're taking the derivative of a function, which is an integral. So that's that fundamental theorem of calculus part 1, where those are going to undo one another. We'll have that negative. So we'll be left with secant, however, not secant of x, secant evaluated at the upper limit of integration, which is the 3w to the 4th power. But again, our integral is actually a composite function, since we're not integrating just from a constant to w, but rather a constant to another function here, 3w to the 4th, then the chain rule requires us to chain on with multiplication the derivative of 3w to the 4th, which will be 12w cubed. So this is going to leave us with -12w cubed times the secant of 3w to the 4th power as my answer for the derivative of the original function.